Welcome to Code Coffee's Intro to Rust. I'm Charles. I'm a full stack developer. I previously worked at Apple and several startups, but I'm also looking for work, so you can hire me.
Hi, I'm Liam. I am a recent graduate of the Master's in Computer Science from Stevens Institute of Technology over in Hoboken. Also a full stack developer. I really like Rust. I'm going to talk. And I have an internship actually the next 4 months, but after that, I'll go for work, so I'm there too. So, yeah, we have a few goals for this presentation. Hopefully learn the syntax and semantics of Rust, explore Rust's ownership model and error handling, which is what makes it memory safe. We'll get into that. We'll understand concurrency, running multiple threads and tasks at once for Rust. And we'll, as an activity at the end of the CLI program, however, you might not have time for that, unfortunately.
But we'll give you the link so you can do it at home, and feel free to reach out to us if you have any questions. So, who here has heard of Rust before? Okay, good amount of you. So, it's what's known as a systems programming language, which means you can write low-level software, you can build parts of operating systems. If you've heard of Linux, part of the Linux kernel is actually being ported into Rust, and a significant portion is currently in Rust. It was first conceived and developed by a guy named Gordon Orr, and one day he was at his apartment building, and it broke. The elevator was broken, and he wondered, this is most likely a seg fault. This is how a programmer thinks. They see a broken elevator, and they're like, I know what's wrong with that. And that infuriated him so much that he developed a programming language that would no longer have memory issues the way C and C++. It was originally, he worked at Mozilla, and Mozilla ran Rust for a while until it eventually became owned by a coalition of both Mozilla, Huawei, I think Amazon, a couple of big companies, but that's what the Rust Foundation is. But basically, the main feature of Rust is that it has memory safety without a garbage collector. And it also is very good with concurrency to prevent things known as data races, which we'll get to later. This is just a meme just making fun of the fact that it has both object-oriented programming and functional programming.
So, why Rust? So first of all, as that name alluded to, Rust supports a mixture of imperative, procedural, concurrent actor, object-oriented, and pure functional styles. It kind of takes inspiration from a lot of different kinds of languages and picks out the best parts of each of them. It solves pain points present in many other languages. So again, as we talked about C and C++, they often have issues with memory safety. But Rust also still maintains performance of those compiled languages. We might say that next. Statically typed. So things that in other languages like Python and JavaScript are not statically typed, which means that you often get issues of a wrong type at runtime. Rust has a very strong type system. It has constraints on the data and behavior, leaving cognitive overhead. The compiler checks that data is in the right shape for you, and eliminates misunderstandings. And yeah, there it is. High performance and low memory usage, despite being safe, like other languages, like JavaScript and Python are. It still has very high performance because it is compiled down to actual machine code, like C and C++, but without those issues. You can see on the side here, we have safety versus control performance. Rust is very safe, like a strong, like Haskell, which is a functional programming language. It has a very strong type system, very, very strong theory, basically backing almost all of its mechanics. But Rust has that amount of safety, but with a very, very high amount of control and performance like you get in C and C++.
So a common problem in C was using after free. So what, in memory, when you're working with C and C++, you can do two things. You can allocate memory with malloc, where you're saying, okay, this variable will have, for example, here, like, it'll be, we're allocating an integer, like, in memory, and when you're done with that, you need to free it so that it can be used elsewhere. But the problem with that is, let's just go through the code here. So we're saying, we're creating a pointer, and we're saying this variable is going to point to a piece of memory. Then on the next line, we say that memory is going to be 42. So if we run this print line right here, it will say that the pointer is 42. The next, we say we're going to free that. We're going to free the allocated memory because we're done with it. But accidentally, we try to use it again afterwards. And that produces unpredictable behavior. It's like rolling the dice. There's a chance you might even get 42, the correct answer. But it could also, it could be anything. It could crash the program, like you don't know what's going to happen.
Did you set that in mathematical melt? Is that like your proper way to run that C? After you free it?
I'm sorry, can you repeat?
I understand what he's saying. He said that if you should set the pointer to null after freeing it, that is somewhat best practice in a way. I've done that in my own C programs, but it doesn't really solve the issue entirely, and it gets complicated if you start sharing memory in different locations. If different variables are holding that pointer, it's going to be freed in one place, and then that other place doesn't know that's been freed and it accidentally uses it.
So one of the big problems with this is that this is a runtime error, meaning the error only happens when you're actually running the program. If you're programming a nuclear reactor and this happens, you have a problem. But if that same program was written in Rust, you would find that problem at the drawing board. You would be frustrated because you're going to spend, I'll be honest, you're going to spend a lot of time in Rust arguing with the borrow checker and ownership rules. But at least if you're programming a nuclear reactor, you're doing that in the safety of your home rather than this just crashing at runtime. So like one of the main selling points of Rust is that you patch things at compile time.
Yes. And so, as an example of that, here is our very first Rust program we can see here, and it's demonstrating the ownership model. So here in Rust, each value has a single owner. And when the owner goes out of scope, the value itself is dropped. And that helps when it issues double-free, dangling corners, and enforces strict ownership rules. This is how it handles memory. So pretty much, as you can see here actually, we start off by making a string at S1. So S1 variable holds that string. And then when we say S2 equals S1, that moves that string to be owned by S2. And so right now it works. If you press the run button on there, you will see that it prints our world because it works there. However, if you tried to use S1, let's say uncommenting that, after you moved it to S2, you're going to get a whole compiler error in Rust. It's going to say that you move the value, and so you can no longer use S1. And so this is basically that there's one place in memory that has one name, and you know it, and the compiler knows it too, so it knows when it is safe and not safe to use memory. It's not necessarily if you pass a variable into a function, it will also then, at the end of that function, it will get free out, and you can no longer use it. You might want to know how to use memory across multiple functions. If you go to the next slide, that's how you can do that. Sorry, it's selected on the play button, wasn't it? There you go. Yeah.
So this is where borrowing comes in. Because you can only have one owner, you're going to need to borrow at times. So there's two types of borrowing. There's immutable borrows, where you could borrow, you can use it as many times as you want, but you can't change it. The way you do that is you just put an ampersand, like the and sign, before whatever type it is. So a key represents any given type, like it could be a string, it could be whatever. But mutable borrowing, you need to just say and mut. And you can only have one at a time to prevent data races. This becomes very important when you're doing concurrent programming. So to walk through this program, first we're saying, let's make a string. A string that we could change. We're going to say let mut, saying that we could change it. So we could do an immutable borrow, where we just use the ampersand and nothing else. We're passing it to a function, calculate length. And here, we can read from it, but we can't modify it, because it's immutable borrow. Next, we have a mutable borrow in the function modify string, and we're allowed to say, what we're doing is we're adding a comma world to that string. So let's run this. And it works.
So, structs. Structs are how Rust groups data together. Similar to objects in other languages. They are immutable by default, as in the variable that we saw earlier. And so if you want to actually make something mutable, you have to do the and mute and all that. Fields can be accessed with dot notation, very similar to other languages too. Fields can own or borrow data. And so basically you're grouping a variety of names and data together. You can actually borrow, say like a field can be a reference to, and also you can borrow from a field. Methods can operate on an instance of the struct. So this is kind of how it takes some information from object-oriented things. You can implement functions for a struct type, and you can call that, and it will call that on itself. So as it takes self as the first parameter. That means that you can access things on that struct that you call it on. And associated functions don't operate on a particular instance. Is there a symbol here?
Which word?
The associated functions don't have on any sorry. Okay, there it is. Associated functions. There it is. Sorry. Yes. So associated functions, if you don't actually give it a self, you can call that on the type itself. So say if you look here, the square function is an example of one. If you can call that with rectangle colon square, then that will return a struct of a rectangle. You can run it here actually. You can scroll down to the rest of the code too, and it will work. It's a long example, so yes, you can see here the associated function you call on the actual type itself rather than an instance of the struct.
Like a static.
Yeah, a static function. Yeah, it's similar to a static function is equivalent to other things. Yep, exactly. So yeah, there's here even walk through the code as well. We have the actual struct up there. It's a rectangle. We make two 32-bit unsigned integers. We then implement some functions for it. The area one is an instance function. It actually is called on an instance already. So it does and self, which means that you can access whatever instance you call it on, and here it returns the times with the height. Hence why down there, when you actually call the area function, you get 30 times 50, just 1500. Yes, sorry, you had a question.
Yeah, I have one question about U32.
Yes.
Is there a reason why it's called that instead of bit 32?
32. The U stands for unsigned. So it's
As in like positive versus negative.
Oh,
So-
okay.
yes, unsigned versus signed integers. That's kind of going along with how Russ is kind of like particular about things. The actual like number types, there's no like you don't just say int. Like you actually specify. You say U32 or I32 or U64, I64 for a 64-bit unsigned or signed.
Instead of saying stuff like
Yeah.
F or V.
F is for floats. There's F32 and F64 as well. But yes, you have to specify, like the actual type name based off of like the, number type and also amount of bits.
Thank you.
In a standard library at least. Yes.
Just a super quick one. I know it's strongly typed, but does it have type inference or is everything like has to be written out clearly?
So as you can see, there is some type inference. A variable can be typed in for, if you call a function, you say let something equals and then a function. It will infer that type most of the time. You have to strongly type your actual functions themselves. So you have to, type your input and your output there. You can't have it infer the output type. But otherwise, it can infer most of the time, and it'll let you know if there's ambiguity you have to specify. Yes. You have a question? Or you?
Yeah. So from like previous slides, does it default by copying through reference, and then when you borrow, you're just copying the value at that time? What happens if you borrow a mutable? If you borrow not the mutable one, the regular one, and then the owner changes the value at runtime, which value is used? The one initial copy, or?
So by default, like if you say like
So like when you did, sorry.
Should we go back to the slide, specific slide?
That's fine.
okay, so yeah, by default, it will move the value unless the value is copyable. That's kind of more advanced than we gotta get into later. So when you kind of like the early like the S2 equals S1, pretty much S2 becomes a new name of that value. It's as I said, moved to it, and S1 is no longer accessible. When you do a reference, it is, and I'm not sure what language you used for yourself. Like it's basically a pointer to that value behind the scenes. And with mutable, when it's mutable, if the owner modifies it and a mutable or somewhere else, like the actual
So
value.
when you're not when it's mutable, like just regular, right? If I borrow a value and
Yes.
then I'm doing something concurrently and then something changes that value, it just
So we have a
Yeah.
concurrency slide. I think
Yeah,
that
we'll get
will
onto that.
probably
We'll get into
explain
that. Yes,
it.
get into that.
Yeah. But
Yes. Sorry. Any other questions? Okay. Yes. So speaking of concurrency, I think that's the next slide actually. That's 2 slides. Yes.
okay. So concurrency is when you're running 2 tests at the same time. And a data race can happen when you have 2 threads looking at it. For this example, let's say that the value is this tissue box. I'm a thread, he's a thread. And we're both looking at this tissue box. But at least one of us writes to the table. If we don't have a lock on this tissue box, we're going to have a problem, because if
I try to grab for it and you try to grab at the same time.
yeah, we have an issue. Does that make sense? Okay. So that's why we have on the next slide we'll have the locks and the mutexes that kind of prevent this. But let's go through this example right here. We have a counter. It starts at 0. We make a function that goes up to 100,000 and increments. Now in the main thread, we have 2 threads. The first one, we create 2 threads that both call this method, and then we wait for them to finish. But we could have a data race because of like what we just said, that There's no lock on it.
Yeah.
So let's see what happens when we.
We can't run it because it's a C program.
Oh.
Yeah, basically it's not going to be 200,000. You would think it would be, but it's not, because behind the scenes an actual thread is going to have to read, update, write the actual value back. And so at different points, both threads can do the same thing. So one thread might read it, other thread will read it. They both update it and write it back. And it should have been implemented twice, but it only does it once because they were reading stale data.
Any questions on that? Okay.
So, Rust has a very strong concurrency model. It has a few type of standard library that help you with doing concurrency. So you have a mutex, which ensures that only one thread can modify the counter over time. It stands for mutual exclusion, if you're curious. And it does, the name says it, basically make sure that whatever holds the mutex can work on it, and it cannot be entered by another thread doing the same thing on that value. Arc is atomic reference counted pointer. That is essentially how you can handle sharing data at runtime. It keeps track of how many things are referencing the data across threads and then routes. Atomic means it can be entered by other threads. And reference counted means that it counts the amount of references to that data. When it hits 0, it knows it is free to drop it because nothing is looking at it and can access it ever again. And yes, locking. The lock method on the mutex is used to require the lock, and as I said earlier, it ensures that only it is accessing it. No other thread can access at the same time. We can run this code. As you can see here in our example, we make a counter, which is an atomic reference counted mutex to the value 0. And then we make two, we make two threads that then run a million-long loop. That in each loop it will lock that reference and then add one to it, and then at the end we wait for them to finish. And as you can see, despite being concurrent, they actually correctly counted 2 million. Any questions on that? Yes.
Yeah, so that arc paragraph up there,
Yes.
is that like replacing, like, that's like an alternative to like borrow technique? It's like replacing that.
It's essentially, it still enforces the rules at runtime. So basically what you're doing is that it's its way of, it's enforcing the rules at runtime, and you can't exactly rewrite it in compile time. At runtime with multiple threads, it will keep track and make sure, you have certain, it enforces the rule of having either all the mutable borrows or one mutable borrow at once. And yes, it keeps track of the borrowing stuff. Yeah. Yeah.
And the reason you can't keep track of it is because it's on multiple.
Yeah, because of multiple threads, you can't exactly say it's impossible to say, oh, I have the correct borrows here because they're running at the same time, they're running at runtime. So here it's going, okay, I'm going to make a reference kind of thing that you can share dynamically and ensure that only one thing is being mutated at once. As you see here, the mutex new ensures that too. Mutex then actually has the lock on it and makes sure that when you acquire that lock with your little counter lock, that it's the only thing modifying the variable at that time. Yes?
Yeah, if you were to modify this code in order to trigger a database condition, would it actually catch it at compile time?
As far as I know, in most cases, yes. Like if you have to lock the mutex here, I don't think you can. You can modify it here that would break
For
that.
example, if I forgot to do the arc clone, will it compile?
Our clone, that I believe would. Yes, but at that point, I think it would move that value into it, and then it would complain because without that line there,
Can you run it?
Yeah, we can try that, yeah. You want to try and, yeah, comment out the let counter line, and you'll get an error pop.
Oh yeah, in Rust, if you want to comment out a line, it's like many languages, just do
Yeah,
slash.
C-like languages that, it also has like the block comments, the /r. Yep, there you go. Yes, so, the issue is that you're moving it and it does not implement copy. It's what we talked earlier. You cannot trivially copy it. And so when it's doing it, it has to move it, and it's like, we can't have this value in multiple places here. I could not easily have this value. It's already in this one thread, and it's being moved twice, and therefore, it does not let you do that. So you have to actually do that manual clone there that says, hey, by the way, I'm making another reference to this value. Okay.
So lifetimes. So normally, when a variable goes out of scope, it's dropped. So lifetimes are how, there's a problem called dangling references. So if you make, in C, if you were to make a pointer to something, and then that memory is free, and you try to access it, you'll have a problem. But in Rust, that's not possible because we have strict borrowing rules. So in this example, we're going to have a dangling reference. But unlike in C and C++, where it's a runtime problem, we will get a compile time problem. It's complaining that we can't use a borrowed of this string in the main function. So to fix this, instead of returning here we're saying what it returns is a borrow of a string slice. What we need to do here is we're going to say, no, we're just going to return a string. But we'll still have a problem because we're returning the return is a borrow. Also, another thing, in Rust, by default, if you just put something at the bottom, we're just returning it. It's not like a language where you need to write the word return. You can literally just do this. But the last step to make this work is we remove the ampersand, and we run it, and we get hello Rust. Now, similar to other languages, we can say something static. We want something to last the entire duration of the program, so we do apostrophe static. In many parts of Rust, you don't need to always worry about lifetimes. It'll be inferred. But there will be times where you need to just say that a variable lasts a given duration, that this variable lasts as long as a different variable, and so on.
Not often I have to worry about it, but sometimes you have to get into that. And then pattern matching. This is one of my favorite features of Rust. Simplifies code by matching values against patterns and executing corresponding code blocks. So if you're in another language, it's like you don't have to do like a if something equals something, then this, else if, else if. This is a very convenient way to kind of do that all a match statement. It's like a switch statement. You can use it instead of a it's if else. And it must cover all possible cases. This is checked for at compile time. If you leave out any kind of case, it will tell you that, oh, this is not for this case. And you either, in some cases, you can cover all cases manually. In some cases, you have to just leave a little underscore that says any other case. That's the wildcard pattern that is there. So as you can see here, we sort of like match on the number, and you can say it's 1, you print 1, 2, you print 2, 3 or 4, that's what the bar means, 3 or 4, and otherwise it'll say other. And this gets really powerful, so we have some other features across that we didn't get into here, things like enums, result types, you can match on cases of like a thing something succeeds or fails. That's how you handle a lot of errors in Rust. And
Just sorry to interrupt, we are running a bit
Yes,
on
we are. We are
time, so
just
we're
using
gonna
it 4
like,
o'clock.
we're gonna like
Yes.
run.
Yep, and that's the last slide. So
Okay.
yeah. Yeah,
So this act that we developed an act, if you want to see these slides, give a QR code and link, and also we have an activity where you could build a text adventure game in Rust.
Yep, it runs on the website, the Rust Playground.
You don't need to install anything, it's all in the browser.
And
Thank you.
yeah, Rust, if you want any further information on Rust, has also a lot of great resources on their website. They have a book that's a whole like great tutorial on how to use it. They also have some like self-guided like exercises, and yeah, it's a very friendly community. So check it out.
Awesome.